Hello everyone, this is Manikanta from ECEB, AIT Tech Talk Signals and Systems. Today we are discussing about design and implementation of initial cell switch in 5G NR systems. Introduction to initial cell switch in 5G NR systems. Initial cell switch is a crucial procedure in 5G NR systems. It helps devices synchronize with the network and identify suitable cells for connection. Efficient design and implementation of initial switch enhance network performance and user experience. Why the initial cell switch is crucial in 5G NR systems. In 5G new radio NR system, the initial cell switch is a crucial step in the process of establishing a connection between a user device UE user equipment and a 5G based station GNB. The initial cell switch is necessary for the UE to find and synchronize with the serving cell, enabling subsequent communication. Here are key reasons why the initial cell switch is crucial in 5G NR systems. Synchronization. The initial cell switch is essential for the UE to synchronize its timing and frequency with the serving cell. Synchronization is critical for the proper reception and transmission of signals between the UE and the base station. Frame, timing and frequency offset. The UE needs to determine the frame timing and frequency offset of the serving cell. Knowing the frame timing is essential for correctly decoding the radio frames, and the frequency offset adjustment is necessary to align the received signal with the correct frequency. Cell identification. The UE needs to identify the cell it is going to communicate with. The initial cell switch involves searching for synchronization signals and decoding cell specification information, such as the cell identity. This identification is crucial for subsequent communication and handovers. Initial access. Once synchronized and identified the serving cell, the UE can proceed with the initial access procedure, where it is establishes a connecting with the base station. This involves transmitting and receiving specific signals messages for access grant and system access. Network assistance. The initial cell switch provides the UE with necessary information to adapt to the network conditions. For example, it allows the UE to receive cell-specific configuration parameters such as modulation and coding schemes, radio resource management settings, and handover-related information. Handover support. Establishing proper synchronization during the initial cell switch is foundation for supporting handovers between cells. This is crucial for maintaining ongoing connection as the UE moves through different areas served by different cells. Beamforming and MIMO configuration. In 5G, beamforming and multi-input multi-output MIMO technologies are commonly used to enhance data rates and coverage. The initial cell switch helps the UE to determine the beamforming and MIMO configuration, allowing it to optimize its reception and transmission patterns. Network efficiency. A successful initial cell switch ensures efficient utilization of network resources by allowing the UE to communicate with serving cell using correct parameters. This contributes to overall network performance and user experience. Key objects of initial cell switch. The primary objects of initial cell switch are synchronization and cell detection. It enables devices to establish time and frequency synchronization with the network. Cell detection helps devices identify available cells and their parameters for connection. The primary objectives of initial cell switch are synchronization and cell detection. It enables devices to establish time and frequency synchronization with the network. Cell detection helps devices identify available cells and their parameters for connection. Key design consideration for initial cell switch. Initial cell switch should be fast and reliable, enabling devices to quickly establish network connectivity. It should be capable of handling large number of devices simultaneously. Design consideration also include power efficiency and robustness against interference. Key components of initial salvage. The initial salvage procedure comprises three main components: primary synchronization signal (PSS), secondary synchronization signal (SSS), and physical broadcast channel (PBCH). PSS and SSS provide time and frequency synchronization, while PBCH carries essential systems information. These components are transmitted periodically by the network for devices to detect and synchronize. PSS and SSS in initial salvage. PSS and SSS are short sequence transmitted by the network. PSS helps devices identify the frame timing and create time reference. SSS assists in identifying the cell-specific identity, providing additional cell information. PSS and SSS are short sequence transmitted by the network. PSS helps devices frame timing and create time reference. The SSS assists in identifying the cell-specific identity, providing additional cell information. PBCH in initial salvage. PBCH carries essential systems information, including cell-specific parameters. It allows devices to identify the ID, bandwidth, and modulation scheme. PBCH decoding provides critical information for devices to proceed with the cell selection process. Timing and frequency synchronization. Timing synchronization ensures devices align their transmissions with the network. Frequency synchronization enables devices to match their carrier frequency to the network. Accurate timing and frequency synchronization enhance overall system performance. Timing synchronization ensures devices align their transmission with the network. Frequency synchronization enables devices to match their carrier frequency to the network. Accurate timing and frequency synchronization enhance overall system performance. Synchronization methods in initial salvage. Synchronization can be achieved using time domain and frequency domain methods. Time domain methods utilize cross correlation techniques to estimate timing offset. Frequency domain method exploit the cyclic prefix to estimate frequency offset. Cell detection in initial salvage. Cell detection involves identifying available cells and their characteristics. It requires searching through a predefined set of frequency and time resources. Energy detection and correlation based techniques are commonly used for cell detection. Cell detection involves identifying available cells and their characteristics. It requires searching through a predefined set of frequency and time resources. Energy detection and correlation based techniques are commonly used for cell detection. Energy detection for cell detection. Energy detection involves measuring the received energy in frequency and time sources. It helps identify cells without sufficiently high energy levels for potential connection. Energy detection robust against interference but requires a predefined energy their hold. Correlation based techniques for cell detection. Correlation based techniques utilize the known reference signals transmitted by the networks. These techniques correlation the received signals with the known reference signal to identify cells. Correlation based techniques provide accurate cell detection but are sensitive to interference. Correlation based techniques for cell detection. Correlation based techniques utilize the known reference signal transmitted by the network. These techniques correlated the received signal with the known reference signals to identify cells. Correlation based techniques provide accurate cell detection but are sensitive to interference. Challenges in initial salvage design. Initial salvage design must overcome challenges such as multipath propagation and interference. Multipath propagation can cause delayed spread affecting timing and frequency synchronization. Interference from other cells or devices can impact the accurate and reliable cell detection. Mitigating multipath propagation effects. Techniques like estimation and equalization can help mitigate multipath effects. Channel estimation estimates the channel characteristics to compensate for multipath distortion. Equalization technique mitigate the impact of path propagation of synchronization. Interference mitigation in initial cell stage. Adaptive filtering and interference cancellation methods help reduce interference effects. Interference mitigation techniques enhance the accuracy and reliability of cell detection. Performance metrics for initial cell stage. Performance metrics for initial cell stage include detection probability and false alarm probability. Detection probability measures the ability to correctly detect available cells. False alarm probability quantifies the likelihood of incorrectly identifying non-existent cells. Design trade-offs in initial cell stage. Initial cell stage design involves trade-offs between complexity, latency, and reliability. Increasing complexity may improve accuracy but result in higher latency. Balancing these trade-offs is crucial for optimizing the overall performance of initial cell stage. Initial cell stage design involves trade-offs between complexity, latency, and reliability. Increasing complexity may improve accuracy but can result in higher latency. Balancing these trade-offs is crucial for optimizing the overall performance of initial cell stage. Implementation challenges of initial cell stage. Implementing initial cell stage requires efficient algorithms and hardware capabilities. Real-time processing requirements demand optimized implementation techniques. Hardware constraints such as processing power and memory must be considered during implementation. Implementing initial cell stage requires efficient algorithms and hardware capabilities. Real-time processing requirements demand optimization implementation techniques. Hardware constraints such as processing power and memory must be considered during implementation. The initial cell stage in 5G NR systems faces several challenges due to the complexity of the network architecture. The use of higher frequencies and advanced technologies like massive MIMO and beamforming. Here are some challenges associated with the initial cell stage in 5G NR, along with potential solutions or techniques to address them. Massive number of cells. Challenge in urban environments, there can be a massive number of cells, making it challenging for the UE to quickly identify and synchronize with the serving cells. Solution: use advanced research algorithms and strategies to efficiently scan for synchronization signals. Techniques such as a beam sweeping or cell specification beamforming can help narrow down the search space. The initial cell stage in 5G NR system faces several challenges due to the complexity of the network architecture. The use of higher frequencies and advanced technologies like massive MIMO and beamforming. Here are some challenges associated with the initial cell stage in 5G NR, along with potential solutions or techniques to address them. Higher frequencies and propagation characteristics. Challenge: higher frequency bands such as a millimeter wave wave band used in 5G have a different propagation characteristics, including higher path loss and susceptibility to blockage. Solution: employ beamforming techniques to overcome path loss and mitigate blockage effects. Beamforming helps focus the transmitted and received signals in the direction of the UE, improving overall quality. Initial access complexity. Challenge: the initial access procedure involves several steps, including random access and contention resolution, which can be complex and time consuming. Solution: optimize the initial access procedure by using advanced random access schemes like non-contention based access and reduce contention resolution time. Implement efficiency signal and scheduling strategies to expedite the connection establishment process. Interference and noise. Challenge: interference from neighboring cells or external sources as well as noise can degrade the quality of synchronization signals. Solution: use advanced interference cancellation techniques and robust synchronization signal design to mitigate the impact of interference and noise. Adaptive filtering and interference aware algorithm can improve the reliability of signal detection. Dynamic channel conditions. Challenge: channel conditions can vary dynamically, impacting the quality of received signals during the initial cell search. Solution: implement adaptive algorithms that can adjust to changing channel conditions. Techniques such as channel state estimation and prediction can help optimize the cell search process under varying circumstances. UE mobility challenge: fast moving UEs may experience frequent handovers, requiring rapid and accurate cell reselection during initial cell search. Solution: utilize productive algorithms and algorithms that consider UE mobility patterns for faster cell reselection, implementing proactive handover strategies to minimize disruption during high mobility scenarios. Beam misalignment challenge: misalignment between the beams of the UE and the serving cell can result in poor signal reception. Solution: implement beam refinement techniques, feedback mechanisms, and beam tracking algorithm to ensure continuous optimization of beam alignment during communication. Synchronization in time and frequency. Challenge: achieving precise synchronization in both time and frequency domains is crucial for proper communication, especially in scenarios with high mobility. Solution: implement synchronization signal with high accuracy and utilize advanced algorithms for time and frequency synchronization. Techniques like frame structure design and synchronization signal processing enhancements can improve synchronization accuracy. Hardware acceleration for initial cell search. Hardware acceleration techniques such as FPGA or ASIC design can enhance initial cell search performance. High-speed parallel processing and optimized algorithms improve efficiency and reduce latency. Hardware acceleration enables real-time implementation of initial cell search algorithms. Conclusion: initial cell search is a critical procedure in 5G NR systems. Efficient design and implementation ensure fast and reliable synchronization and cell detection. Overcoming challenges and optimizing design trade-offs key to achieving optimal initial cell search performance. Thank you.